I think 30.
Which one? The big one? I didn't think so.
Huh?
He's not gonna drive.
Oh well. I know how you do 35 already. But I ask him just in case. 35. I know. Huh? No, we asked him about. Yeah. I don't think. I already know how you 35 though, so. No, I asked him about 35. Like this, yeah. Yeah, but he didn't answer my question though. He didn't really answer my question when I asked him though. Remember? I just asked him about it. He was like, you just know, or he was some shit like that. How about number 55?
355.
355? Which one?
No, 355. Yeah, that's what I'm asking.
Which one? Which letter?
What was our question? It was just like, yeah, that was when he put like. Wait, which one's 36 minus 24? Is there 36 minus 24?
36 minus 24.
Alright, any questions?
It's 354.
Yes.
Can you do a problem for me? 3-54. It's one of the practice problems that you gave us in the study guide.
354. Okay. What's the problem with the problem?
It says 36, positive 36, plus negative 24.
36 plus
Negative 24.
negative 24.
And it says to perform the operation, and it says using sine 2's complement representation for the negative numbers.
Okay. What number is this?
54? 3-54?
Okay. So what's your question about?
When do you fill in the back or the front? Am I explaining myself?
No.
Okay, so you see how 36 fills in like 1, 0, 0, 1, 0 or something like that, right? And the 24 is like 1, da 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 da, and there's like it's one less space than the other one. Do you move it this side and then add the 0 at the end, or do you? Am I not explaining myself again?
So go back. Let's go back and review how to do 2's complement. I think that's your question, right? You got to sine 2's complement number, which is what 2's complement is, right?
Yeah.
I think she's asking when you make 36 into its binary form,
Yes.
and you make 24 into its binary form, instead of marking the spot where it would be 2 to a power is 32, you would only mark it up to 2 to the 4th power is 2 to the 4th power is 16. So it's one less. She's asking if we have to pad it on the left side or on the right side with 0.
Oh, that problem.
Yeah.
Okay, so this is the one where, okay, so there's two different things. Okay, I think I understand the question now, right? So if you have a number, any number.
I got like a big number. Mine is like 7.
Okay, so you have some number here, but it's only 6 bits.
Yeah.
And so you're saying that if I'm not going to operate on a larger number, how do I pad it? Zero fill or extended, is that the question?
Yeah.
Yeah. It's how you changed
Yeah.
Okay.
camera. Something like this?
So what? So we got everybody involved here. What is the consent? What is the way you would do it? Who would want to volunteer how they do it?
I think you would extend it at the zeros to the end.
So somebody says we add zeros to the end to extend. it.
No, other
No,
side.
like on the second number. Or, you know what I'm saying? Like you're doing like
Well,
a
yeah, I'm
subtraction.
pretending this was the second number.
Oh,
Whatever it happened to be. So we said it was only 6 bits in this really weird example. I didn't try to do 24 off the top of my head. But you're just saying that, hey, if I really needed to work with 7-bit numbers or 8-bit numbers, I would just add the zeros at the
Oh no,
end. is what you're
Yeah.
saying.
this is 6
yes.
4.
That's what I'm saying.
Yes.
That's what I meant.
That's 6 4.
Would you put a zero between the sign bit and then the first like value carrying
I don't
bit?
even know. I think it's a 3,
A zero like right there.
Oh.
but I might be wrong.
So the question is, why wouldn't I put the zeros here?
2 years ago.
Oh, that's
So think about the number.
Sorry.
All right, this goes back to how we convert this, right? But before we do that, let's just do one quick review. Which number is larger?
No 6.
This is the larger number, right? It's a smaller number. So that means, right, that if I had 1, 1, 1, 0, 0, 0, 0, would that be a larger or a smaller number than this one?
Smaller. Smaller.
We think that this would be a smaller number because,
It's negative.
More negative.
yeah,
More
these have
negative.
more value, right? These have more value. So that would be correct. So armed with that knowledge, if I wanted to not change this number by putting zeros either at the end or putting zeros way up front, which would affect the value more?
You put to the left.
The front.
The front,
Yay.
Oh,
right? Because that will then push these way
Left,
off
front,
here and
same.
make this number
I knew
much
the answer.
smaller.
I know it.
So we don't want to make it smaller. We want it to stay the same, so adding these bits at the end doesn't change it. Because if you visualize it, that's the radix right there, right? So the further away we get from it, there you go.
Wait, but what happened?
That's your question?
Wait, I have a question.
Yeah,
So like, no, mine is okay.
it's all right.
Alright, so if you add 0 to the right side,
Uh-huh.
wouldn't that make the one at the far left, like, instead of being like 8, it would be like 16 and 32, like, wouldn't it shift the value to be higher?
What's the value of this one?
From-
2 to the what?
Two.
The sign.
Let's find this one.
Okay, now I know, I get it, okay. But what if there wasn't a radix point right there?
Well, there is though.
But without the radix point, so it's gonna,
This is a negative number. The fact that it's a signed number tells us that it very much has a radix point.
oh, okay, gotcha.
What if it wasn't signed?
If it was an unsigned number, then what do you assume about the value?
Then we don't put
Positive.
negative or positive, right? Wait, never mind. Let me figure this out. So if it's unsigned, right?
If it's an unsigned number,
Just subtract, just
what is
subtract.
your, this is a good number, this is a good question though, this is a very good question. If you're told that you have an unsigned number, what do you then, how do you then evaluate the value? How do you determine the value of this number if it's an unsigned number?
Only positive.
Yeah, you assume it's positive and you calculate it as a positive number. Which would then be 2 to the 0, 2 to the 1, 2 to the 2, and so on, right? So just as soon as we introduce the information about this is a signed number, then yeah, it has built into it the fact that it's a positive or a negative number, and therefore we know if it's to the left or to the right of the radix. And that's why I cared about the zero extension on assigned two's complement number. Okay? Good questions. Other questions?
Okay.
Yes?
For problem 335, it asks transforming for the fourth edition, table 3.8, making what that table is and assigning priority to, I think, D0 as the top priority. I was just wondering how you would do that, how you would transform it into its table, because I have the answer, but I'm just confused on how to get it from the table to the original.
Okay. So the problem number again is
3-35.
335?
Yes.
Okay.
Ask me.
So as I'm pulling that up, so we'll look at this. Who walked through this? Who thinks they understand this? Or who wants to understand it better?
I want to.
Anybody want to walk us through this discussion? But he's going to put up the answer here, so you can't go too far afield. We're trying to roll this together, right? So I'll hold it. Okay. 3, 4, 5, plus, 5. All right? So 335. Who thinks they understand this enough to try to walk us through this?
What's the question?
So the question was, how did we get the priority map from this? Right?
It would be to that.
Oh, I'm sorry, you said how did I build the table itself?
Yes.
Oh, so yeah, I was asking more about, okay, given that this is a priority, right? And I gave you the table, then I was asking these questions, but you're going back and you're asking more fundamental question, that is, how did I derive this in the first place?
Yes.
Okay. Let's hold that one until we exhaust the questions first. So I want to make sure we get to everybody's, yes?
Can you do 3-43?
What is below it?
The one right below it.
343. Consider D as the data input. So D is our input, and A0, A1 as our selects. For any combination of A0, A1, and E, the value E is distributed to corresponding outputs D0 to 3. Right. So the question then becomes, how do you determine your D outputs based upon this input set? All right, fair enough. Again, I'm going to throw it out here to the group. Anybody who thinks they understand this that wants to try to walk us through it? Brave souls, you all studied this. You're all ready for it, right? And some of you actually think you got it. Some of you just have lack of confidence. I know you. I know some of you know this one. Really wants to try it, huh? Aw. Okay, so select lines. What's the deal with select lines? How do select lines work? What is their function in life?
Oh, I should know. but you should do it for the class anyways.
That does remind me, right, that when you're asked to define something, you can never define something by itself. Nice try. So what does it mean when we say A sub 0, A sub 1 are two select bits? What does that mean? It means there's some pattern, right? That pattern is what?
The E. Wait, the pattern?
No, it's not the E. The pattern is not the E.
It's the A1, A0.
A0, A1 are select lines, right? So the values of those two input lines,
Affects the output.
right, have some pattern to it. What's that pattern? Yeah.
I'm taking a crack at it, but they determine whether, depending on how it's wired, A1 could determine whether D0 or D1 is used, and A0 will determine whether D2 or D3 are used. So they switch between one of the two.
That's the enabler, right?
Well, so it's a binary number, right? We're going to create a binary number with A0, A1. Did I do 0 and 1 reverse? Yeah, I did. Because it makes much more sense for this one to be 0 and this one to be 1, right? Because they're simply going to start counting. How big of a number can I create or count to with 2 bits?
They kind of figure it out.
Okay.
So E corresponds to like 0 and 1. That's going to be A1, A0 are like the selectors. So what happens is whenever the corresponding number, it'll be 0, 1, 2, 3. So it's 0, 0, it's 0, 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. So whenever it selects 1 and the corresponding numbers match, then it'll show up right there. So in the example, when it shows up A1, A0 is 1, 0, you see right there that it's 1. You see that on the third, on the D2, 0, 1, 2, on the third line, it'll show up as a 1. So it's just kind of reading it as if there is a 1, and then the selector will tell you which line, either D0, D1, D2, or D3, where the 1 will go in that specific spot.
The results of E. Yes, it will select which output the results of E is going to be sent to.
Yeah.
We have a name for this kind of a device.
Enabler.
We've looked at these kinds of devices, wiring-wise, logic-wise, circuit-wise. Now you're just looking at the state table, and we have our selector bits, right? And just like he said, 0, 0, 0, 1, 1, 0, 1, 1, which is 0, 1, 2, and 3, is selecting D0, D1, D2, D3 to be the output line for the input, which is E. So whatever E happens to be, 1 or 0, based upon A0 and A1's values, is going to get sent to that 1 or 0 from E input to D0, D1, D2, or D3. What's the name of this device?
Multiplexer.
Is it a multiplexer or a demultiplexer?
Demultiplexer.
Demultiplexer? Multiplexer. It's going from 1 to many.
I'm gonna say demultiplexer.
I'm going to say demultiplexer because
It says it above.
let's see if we can understand the logic, though, right? Because how many lines do I have coming in?
1,
1. How many lines do I have coming out?
4.
4. Okay.
So
if I'm going from 1 to 4, then that meant those signals were multiplexed on that one channel going in, and we're demultiplexing them to their respective channels coming out. If I wanted to take 4 input lines and squish them down into one output line, then I'm multiplexing those multiple lines into a single output line. Yes?
There's only one line.
Technically, there's one input line. I'm using my 2 selector bits to choose how to demultiplex this. But the data resides on just one line coming in. And so that's a very, very important distinguishing point that we don't talk about here, but you'll see it everywhere else. And that is, you have 2 kinds of lines here. You have this is very important to understand because this is the way that you'll be talking in all of your more advanced circuits. So we have a data line. And And that's the one we've been focusing on. We have data coming in from one line, it was all multiplexed already as that one input line, and we're demultiplexing it out to 4 output data lines. And then I use control lines to select which output to go into, or in the case of multiplexing it, which one to select input from. Okay, so 2 kinds of lines. I have data lines and I have control lines. Data lines, obviously, that's where we're passing the data through. Control lines is how we affect the circuit. Okay, so yeah, that's how we read this here. If you look at it, you can see, just certainly picking a couple here, where I have 1 and 1, and that means D3 is enabled. Input E was 1, so I put the 1 to the D3 output line. 1, 0 would be D2. So there's D2, because this was enabled, I should say the input line had a 1 on it, so I pass it through. In the case where my enabled line had 0, even though I selected 1, 0, it's passing that through. It's passing that through as a 0. And 1 and 1 comes through and passes it as a 1. So that's what this table is doing. Now you'll never forget the difference between multiplexers and demultiplexers, right? Yes.
Okay, you talk about overflow in the problems, but you never said which one has overflow. Can you do an example where there's a subtraction and there's overflow? So like I can see visually what an overflow looks like. Yeah, it's those.
Okay. Did overflow occur in any one of those?
What about B? It's supposed to be positive 2 and you have a negative 2. Or I don't know what it is, but that's a negative.
Oh, yeah, I see what you're saying.
This B here?
Yeah?
Yeah.
Yeah, what? That's the right answer? I'm confused.
Okay, so B, I had a negative 2, right? So that's 2's complement implementation of a negative 2. Then I has a positive 4, right?
Yeah.
That's
But
a
it's a
positive.
minus, right? So I gotta change it. And when I actually do this addition here, I didn't have any overflows, but I put this 0 because of what reason?
It's a sign bit or sign number.
No.
No? Why? I'm starting to doubt myself. Okay, why? Tell me why.
Anybody else tell us why?
They do it because you need to extend it.
I didn't need to extend it because I had to have 5 bits up here, right?
Yes, you need to.
So I need to use the same size words when I'm doing my additions and subtractions. So I had to 0 fill it to make that happen. So that's not a case of an overflow, but that is a case of a 0 fill. Yeah.
Going back to extension, how do you know whether or not to extend it from the front or the back? Because if you look at 352, or if you use the example above,
Yes.
D, right? So you want to add the zeros and then flip them and then add the 1. Or flip them as in like change the zeros to 1s.
Right.
And then
Convert
add-
it to 2's
Yeah,
complement.
convert it. So why would you, in that case, add zeros in the front versus extending it to the back?
So it's not extending. I'm adding a 1 to it, right?
In which example, D?
No, that's not what D's doing. In the case of D, that was a case of an overflow.
Am I right over? Why? I don't see it.
Why's that? Yeah, I don't know why.
Oh, because it's positive, it's supposed to be negative?
Yeah.
Gosh, I'm so smart.
But if you look at C, it's hopefully C is really obvious, right?
Yeah.
That's also overflow?
So C
No, C is pretty important.
No, it's a positive number. And I've got to subtract or add a negative number to it. It happens to be the same value. Now, here's the difference in two's complement. Oh, actually, come back. What's the difference? What are the two biggest differences between one's complement and two's complement? No, I do have negatives.
Between what?
What are the two biggest differences between one's complements and two's complements? Yes.
Zero value.
Zero value? What does that mean?
One complement is.
This negative or positive? Oh, I
Yes?
one's complement has a positive negative 0 and two's complement doesn't.
Correct. One's complement, I have two representations of 0. I have a positive and I have a negative representation of 0. Two's complement, I don't. I have just one representation for 0, which enables me to do what? What does that enable you to do? The advantage, what's the advantage of not having to use two different representations of 0? You get an extra number that you can represent with the same number of bits. Right? Because two's complement, one's complement, they're both going to use the same numbers of bits. But if I'm only representing 0 once instead of twice, that frees up one of those representations, one of those patterns of bits, to be some other number, other than the other representation of 0. So what is that other number? No, it's not 4.
It's not 4? There's something with the 1. Come on, guys.
What was the question?
It's one additional negative number. So in 2's complement, if I can represent 126 positive, then I can go down to negative 127. Because I choose only one representation for 0. So I choose then to do that other representation, i.e. the representation of minus 0. Instead of being 0, it starts with minus 1. Which means it can go, instead of stopping at minus 126, it can go all the way to minus 127. So if I were to ask you the range of numbers that 6 bits in 2's complement can represent, you would tell me that range of numbers is?
Negative 127 to positive 126. Wait, negative on 2's complement? No?
It's 4 bits, right?
Oh, then I don't know. It's 4 bits.
I have 4 bits, 2's complement number. What are the range of values that those 4 bits can represent in 2's complement? Yes.
So it's negative 8 or 7. Negative 8 to 7.
Negative 8 to 7. The negative will always be 1 more than the positive. And you've probably seen that, right, in some of your earlier courses, and you're just saying, oh, I just got to memorize that, right? I just got to memorize that. My range of numbers is minus 128 to 127. I don't know why that is, but that's what it is. Right? You just memorize that. Well, now you know why. T's complement representation, 1, 0. Okay? Other questions?
So that's the only one that has, those two are the only ones that have overflow? C and D? Oh, all the ones that have a 1 red. It's just that on our paper it's not red.
On your paper's not red.
Well, I didn't print it, so I didn't see it red.
Well, if you printed it in black and white, then it could jump out.
Yeah, so I wasn't sure.
I should have.
Is it red on the thing?
It's not.
It's not red on, is it red on the,
I think
You
it's
look
on
at
the
it
side.
online.
Mine's-
it's red on the side? Okay.
Yeah, if you look online, though, it's red. If you print in color, it comes out. I should have made it bold.
No, it's my bad.
Well, no, I know better, because some people are actually colorblind. I feel bad that I didn't. So some people are colorblind, but everybody can distinguish bold from not. Other questions? By the way, I want to thank you for two things. One, for asking questions and being interactive, and two, you make me feel better sometimes. Lousy. Until now. Other questions? Huh?
I'm ready for the test.
Ready for the test?
3-35?
When it comes, you're going to be ready to
Wait, what?
rock it.
Can you still do 3-35?
Yeah.
3:35?
Yeah, they wrote on the board. You said we do it later.
Oh, the one for the deriving the table?
I got you.
Do you want me to try and do it on the board?
No, don't do
I don't know how to do
that.
it, but I can try.
What's that?
Nothing.
Yeah, this is the only one I
Have
Nice, go
somebody
ahead.
try and do it. Or you don't want to go over it?
No, I really don't want to take the class time on that because
Yeah,
I'm
it
not
makes
going to be
sense to
asking.
talk about it.
That's one question I'm not going to be asking in the exam. I know that much. So.
Oh.
335 is not gonna ask.
Free
Yeah.
one. That's not going to be on the test, people.
Careful. 335. The question that is 335 is testable. The question behind deriving this table, I'm not going to test you. I know I'm not asking that question. It's something you do need to know. But there's other ways I can test your basic knowledge about this.
Wait, so but how do you get the table? Like how? How do you get the table?
How do I get the table? Well,
Yeah.
I can do it one of two ways. I can either from the circle or from the function equations.
So you just plug in chat? I'm kidding. Okay, gotcha.
Yeah, I just from the I can do it either way. I can either start with this and derive the table, or I can start with the circuit, which is what they did, was what your author did, I believe. Start with the circuit and then derive the state table. And I think the biggest thing to let me ask you this question. So I think the question that you're really asking is, how does the priority encoder make this change values? Is that the question?
Around that line, yeah.
On the right. Okay, so in this, you can equate it. It's similar to this kind of logic here, right? Where the priority scheme is kind of like a selection scheme, right? Where it's saying, hey, if I have, except in this case here, if I have a tie, which is really what this is doing still, if you want to think of it that way, if I have a tie, in other words, I have something coming in that I need to then encode, right? Instead of going down path A or path B, my priority encoder is going to absolutely select one, okay? It doesn't mean it's going to override any other case where there isn't a tie. That's the difference between a priority encoder and this type of logic, is that if the selection circuits themselves are unique, there is no need for a tiebreaker, then it is what it is. But it's in those cases where I can have multiples, that's where these don't care bits come from. But the priority bit comes into play. You know, it says high order, low order, whatever it's decided to do. Then based upon that, I just go ahead and set up all my different states, look at my circuit drawing, figure out the values, create my table. Yeah.
What do the outputs A1 and A0 mean for that truth table? Or are they just like static? Because you just flip basically the priority from the book? The truth
Yeah.
table?
Yeah.
Okay, so then just reworking so.
So highest priority is the one on that side, and lowest priority is the one on this side.
Highest is the D0.
Lowest is always 0. It's not left or right, it's 0. 3 is bigger than 0.
So
In the table for this original question, it says like the highest priority is the highest numbers, or like highest
Yes.
subscript. And now for this one, I want you to flip that
Flip it,
and then
yeah.
figure out the circuit.
wait.
Yeah.
So what do they don't cares even do? Are they just there?
So we saw some examples of don't cares, like in our BCD.
Mhm.
Encoder, right?
Yeah,
Byte
yeah.
encoder, right? BCD encoder says, hey, I have 4 bits. I can generate an unsigned integer. I can generate the range of 0 to 15, right?
Mhm.
But my BCD can only take in the values of 0 through 9. So the values of 10, 11, 12, 13, 14, 15, I don't care what they are. They can be set, they can be cleared, I don't care. The purpose for having them marked as don't care instead of forcing them to be 0 is because it enables me then to look at some ways of optimizing my circuitry. So if I can remove some gates and still get the right values for 0 through 9, even though 10 through 15 might get set or cleared, if I don't care about it, then I don't care. And I could then create a more simplified circuit with that. That's why don't cares are important. Yeah,
Can we go back to 3-53?
back to 353.
And number B.
Number B as in Bravo?
Yeah, so the original number is 11110 minus 1110, and we want to extend the second number to 5 bits.
Yes.
But look at the second number, 1110.
Yes.
It is negative 2. But if we add a 0 at the end of it, then it will become negative 4.
If it's
Bless.
a negative number, adding a 0 at the end doesn't change its value. At the right end.
For,
It does.
for 2's complement, it does, right?
So I have 2 people here just challenging me on this in 2's complement. What do you think? Does it change the value too?
For negative or for positive numbers?
Oh, so wait.
Negative, you want
So
to pad it
if it's
on the left.
so it's negative, isn't it like supposedly the mark? What's it called again?
The
The
sign.
radix?
Radix mark in front.
Right.
So it's negative, so it has a radix, imaginary radix sign in front, right?
But does that make that a decimal?
Wait, did it?
Does that make like a fractional number?
No, it
For a
doesn't.
negative number, right? 2's complement. Did we so is this one, actually I'm going to come back for a second, 353, 354. Was this one the sine 2's complement, or was this one? This one was sine 2's complement.
That one's signed, yeah. The bottom one's signed.
Right.
That is signed too.
353.
Both of them are signed. The 150, the one upper one, it's unsigned.
Say again?
The problems above are
Are
unsigned.
Unsigned, right?
Yeah,
353 is signed.
It's signed.
yeah.
That's-
And that bottom
That's what I was
too.
trying to remember. I was working from my memory, which is sometimes a dangerous thing to do. So, okay, so these were sine 2's complement?
Yeah, it says.
Okay.
Yeah.
Yeah. Is the extension of
All right. So in a sine 2's complement world, what is that number? First off, the one without the red. What is that number in a sine 2's complement world?
Negative 2.
Negative 2.
Okay. And if I add the 0 to it, what is it?
Negative 4.
Negative 4. Okay. And what is it we're supposed to be doing?
Positive? Wait, what? What?
No, it's
Use extension to equalize the length of the operands.
So is it like negative 2 minus minus?
Yeah.
Or plus 4?
Yeah.
That's what it's doing.
That's what it's doing.
So it's,
Minus,
you
minus.
see how the top is negative 2?
Yeah.
So if you minus a negative 4, it's like minus and minus make a plus.
No, that's not the question we're discussing.
Oh.
So, if it's the original one is 4-bit number, right? The 4-bit number, if it is a signed 2's complement number,
Right.
is negative 2.
Right.
And here we add a 0 at the end of this, we change the number to negative 4. So I have no problem with negative 2 minus negative 4 is equals to plus 4. That I have no problem with that.
Mhm.
But I mean, in this number, in this question, are we supposed to change the number's value?
Not supposed to change the number, it's to change its sign. because you're inventing the operation, right?
Bless you.
You asked about the added zero.
That you mean is
Yes,
negative?
I'm asking about why we add a zero at the end. Can I?
Yes.
I was wondering about that too.
Choose your turn.
Yeah.
So the original number is 11110 minus 11
Who's raising?
minus 1110.
Right.
It's originally 4-bit number, right?
Mhm.
So if it's a complement, signed 2's complement number, it's -2. This one is also -2. So if we use decimal computation, then it should be 0, right? But now we wanna extend this number to a 5-bit. In here, we add a 0 at the end of it. We change the number to -4, which changes the result to +2.
Yeah.
So my question is why we add a 0 at the end of this number. So in my opinion, if we want to change a 4-bit number to a 5-bit number and still keep the value, we should add 1 before it. 11110, this is still -2.
Okay. Well, everything you said so far is true. What was the question? Not
Are you
your
asking
question.
why you add the zero at the end?
No, not the question. What was the question?
Oh, I can read that to you.
35.
Yeah, 50.
It's to repeat arithmetic from 32, but doing the numbers as signed numbers, and then extending.
Sorry, say it again. I wasn't.
So 3-52, I want you to do
53.
I know, but the first, so it depends on the first one. So they give you
Okay.
some numbers to add and subtract.
Yep.
And then 53 says do that again, but say that there's signed instead of unsigned.
Right.
And so I want you to extend the bits to make them like the same amount of bit numbers,
Mhm.
without doing a loss of precision when you extend it.
Correct.
So for like signed negative number, you should put the 1 at the left side.
So but what was B asking? So B was asking what to number? Did it ask the number? I don't remember right now.
It's,
was it asking it in decimal form or was it asking you for
Why
it
you showing
in binary?
It's giving you the numbers in binary.
I have the pictures.
There you
I have the book.
Yeah, I have the book open right now to that question.
Okay, thank you. This is one of this operation. That's what I was. Assuming the numbers are already in two's complement use extension. Okay. For some reason, I was thinking that was.
I don't know.
Okay. So given, okay, now we got that, now that I got it straight. What this question was. So we were given B, which was represented without the extension because it says to use extension in for 53. We had just the 1110, which was, as pointed out, A2, right? So the question is, okay, if I'm going to use extension, like 353 is asking for, what should we have done for this?
Yes, so it's pretty much saying that B is wrong.
Yeah. Right.
So no matter what, we should add, we're supposed to add a 0, but we have overflow, so it's correct.
No, because we changed the value of the number, the way this is shown. Yes.
So for a B, it says that the final answer is 2, but there's a 1 in the front, so it shouldn't be negative for B.
So we were given the number 1110. So forget about how you interpret that in the previous problem. Given that bit pattern there, and given the definition now that this is representing a signed 2's complement number, do the math. Okay, but before we do the math, let's convert this to decimal first, because that way we can at least understand whether we're doing the math correctly or not. So if this is all I have, these 4 bits here, and I'm told that this is a sine 2's complement number, what number is this? What value is this? -2. We all agree on that. Just kidding. Okay? And I think everybody agreed the above was also -2?
Yes.
Yeah. So from a purely decimal arithmetic operation, our result should be
-4.
4. Yeah?
Wait.
It's
It's
Or
minus.
subtracting.
But it's minus. Thank you. Right? Minus plus 0. And since this is 2's complement, we only have one representation of 0. So we know what the resultant bits should be, right? What should the resultant bits be?
0, 0, 0, 0.
4, 5 zeros. And we know the top one, which is already 5 bits, is 1, 1, 1, 1, 0, right? So the question is, if I'm going to zero fill this number to make it -2 still, so that when I subtract this number from this number, I get this number, where am I going to put that 0?
It doesn't
They want
say
you to extend
zero
it, not to
fill,
zero
it's
fill.
an Extension.
Extension. Thank
Yeah,
you.
extension, not zero fill.
I intentionally use the word zero fill because the words zero fill and extension is something you should be able to translate knowing what numbers, what kind of complement you're using, right? So I want us to see if we understand how this works, because then, given whether you interpreted the word correctly or not, you know what you're doing, right? So if I wanted to, forget what the word is and forget whether that means it's supposed to precede or antecede, where would I put this extra 0 that I need here? I put it on the end, and everybody got upset with that. Rightly so, by the way. So if I don't put it at the end, where does it go?
You should extend like a 1 off to the left side, because that's the same as the sign for the.
So if I put it there, when we
No,
do
but that
the
should be a 1
operation,
to extend,
Should be 1.
because that'll keep the same precision as a -2.
Well, that's gonna make it positive when you put a 0 in front. Oh my
Yeah.
god!
You can't zero fill it anywhere without changing the number and making it wrong with this form of number system.
Wait, so you put 1 in front instead?
We don't
But it's a
zero
0
fill
fill.
it.
You
You
can
don't
only
use
use
extended.
zeros. You can't use ones.
Oh, gotcha.
If
Gotcha.
you want us to zero fill it and get a different number, then we can do that. But if you want us to zero fill it and get the same number, that's not possible with this number system.
At the end of chapter 3, we have extension examples, and if it's a negative operand example, we put ones before it,
yes.
not 0. We don't use 0.
We use 1s. Yeah, but what if you want to use 0s? You don't? I just don't like it.
What is that number?
-8.
That's
Yes.
8 plus 6 now.
What?
46.
-8.
-8. What is that number?
-8.
That one.
-8.
Yep. Does it hurt me to prepend this with a 1?
No.
If it's a negative number? No. They all say the same, they're all going to translate the same number. Okay? That's why when you're working with negative numbers, you can prepend it with this 1 and not change its value. So if you have 4 bits and you need 5 bits and this is a negative number, sure, prepend it with a 1 because it doesn't change its value. Now, 1, 2, 3, 4, 5 bits, I have these all aligned, I can do the subtraction, and it looks like it's going to go to all zeros, doesn't it? Yes.
So then why just brings it back. So why didn't?
Because I was waiting for emails from you guys.
Really?
Yeah, I intentionally threw that one in there to see if I was going to get feedback from the study groups.
So it's actually 0.
That one.
We fill it.
Actually,
So then, what about D?
Yeah,
Should we also just put 1s
Yeah.
in front?
Yeah.
I would have failed that test.
No, that's why we're here tonight.
Okay.
That's what I was asking about extension because I saw it like go to the left and to the right, and I was like, okay, is that have to do with sign it or not sign?
Which is why I started off our discussion by not answering it directly and talking about this.
I went in and answered them.
I know you want to. I want us to think about it because if you think about it and you understand the number systems,
Like,
you will
why
not
would
get
you
them
do
wrong.
that?
Even if you get tripped up on the language.
Yeah, I know.
Thank you for asking. I wasn't going to let you leave tonight unless somebody asked it. So. Okay. Other questions?
Is there another trick in this
Yeah, that
test?
was
that we
the
should-
only
Okay.
I thought that one was, I almost didn't put these answers in here because there's all these calculators all over the place, right? But I realized that some of you, I think, were still struggling with the whole one's complement versus two's complement issue, and so I went
So-
ahead and put something in there. Yeah.
Which one has overflow? Now I'm getting confused.
Now, okay. What's over?
On this,
What's overflow?
no, not the sign. On the sign ones. It says we have to we have
Oh, for the
to.
last one?
Yeah, it says we need to tell whether there's overflow or not.
Oh, you-
On that, no. The one we were, those.
So when would I have an overflow condition? What causes an overflow to happen? Yeah.
If you get too negative or too positive for your like word size or whatever. Like if you
Negative
like if you're doing
for
if you, I
word
think
size.
if you're doing like a byte, if it gets lower than negative 127 or greater than negative 128 and greater than 127, then you get loss of
You need
precision.
to generate, yeah, if you generate a value that's too large for the number of bits,
Mhm.
yes, that's the definition.
Okay. Got it.
Other questions? All right. Sure, no other questions? The rest- Now remember, these were some sample questions, right? And this is a study guide, but this doesn't mean these are the questions even with different numbers that you're gonna see on the exam. I know that exam number 1 looks an awful lot like study guide number 1 because I was a little fearful of this class because you were so quiet. Okay, so I did that for you for exam 1. You've had some time to warm up to all of this, time to get more familiar with the topic itself. That I am going to be introducing some things in exam 2 that aren't necessarily on this particular study guide because, as I keep reminding you, terms are testable.
Not the
Right?
terms.
Not that too.
The terms.
Terms are testable, and there were some key concepts that we focused on pretty heavily in lectures, and we certainly have in the slides, and right out of your readings, I kind of walked you through some different examples or different ways of working on some of these problems, okay, just so you would hear 2 different approaches to solving a particular problem. So anytime we spend a good deal of time on a specific subtopic, that is testable, okay? Put these questions in here because certainly these key concepts and the concepts behind deriving some of these solutions are important and are testable. Okay? These were just some sample problems to get you digging into. Right? Other questions?
What are the terms?
Okay. It's been a 2 minutes then. Making some progress on chapter 4. we talked about that. We talked about that. Let's talk about that.
I think so.
So everybody remembers about memory, right?
Yeah.
I'll take a little bit on too, but
We talked about it, we had some examples, we showed how it works.
Are you testing us a little bit on chapter 1 too?
So, one of the
testing
things
us a
that
little
comes
bit on
up in
chapter 2?
usually one
Chapter 2, a
discussion
little bit more.
is
Oh,
that,
okay.
okay, so we're looking at this thing, we have the ability to inject these delays, we've got this clock, it's helping to synchronize things, it all kind of makes sense, except now we've got this little nagging voice in our head, right, that's telling us like, the circuits have delays, and some circuits have more delays, or some components, right? All circuits have delays, of course. All components have delays, and the circuit is a sum of its different delays in various combinations. But some components have different delays than others. Okay, and sometimes we actually inject some delays, like that inverter that it has. Well, we need the inversion. But if I had fed that into like an AND gate that had an AND input, an inverted input on the delay there, then I would have fed an inverter into an inverter, which was introducing a delay, just introducing a delay. Could have done it. Okay, but that's just an example to get you thinking about what these delays mean. Okay, all these components have to take time to switch. And we saw them in your more primitive forms when we're looking at transistors early on, right? And that hopefully you flash me back to that and say, oh yeah, that's why we have delays, because electrons are bumping into each other, and that takes time. Okay? So then we have some questions that start popping up, right? And that is, there's some combinations, given that we have to be worried about delays, there's some combinations that might seem problematic, okay? And of course, everybody looks at the title first and they say the glitch. Well, this sounds like fun. We're going to look at something that's a flaw, right? That's what a glitch is, right? A flaw. Oh, we're going quiet again. So, yeah, that's what most people think of when they say glitch. It's a flaw. Well, sometimes those flaws can be put to our advantage. We can use them as part of our design work, okay? So let's see if we can understand and create one intentionally, okay? So let's take a look at this very simple circuit here with this XOR gate and this AND gate, right? And then we're gonna have three inputs feeding these two gates here. We've got B and C going into this AND gate here. We've got its output being XORed with A, okay? Pretty straightforward, we think we understand. Okay, so we, for this very simple example here, decided, oh, let's put A, B, and C all from one source. So if A is 1, then B is 1, then C is 1. If A is 0, then B is 0, then C is 0. If C is 0, then B is 0, and A is 0, right? You got the logic. Pretty straightforward.
Yeah.
Okay, so it's just one source, okay? So the question is, if they're all the same, value, then isn't X always going to be A or B or C? Or its inverse? Right? Let's just take A. If I have A, let's say I had A and B and C were 0. A went to 1. It goes in the XOR. B and C would then be zeros. And so X would turn to a 0. So my 1 would turn to a 0. Everybody would be happy. Problem is, if I turn A into 1, then B and C are also turned into 1. So B and C is going to produce a 1 out of the AND gate. And that 1 would get XORed with A, which would set X to 1, right? Because X would only get 0 if A were 0 or B and C were 0. Or if B and C were 1 and A was 0. We have to have one or the other, exclusive or, right? So in the case of A, B, and C all zeros, X is 1. In the case of A, B, and C all ones, it's still 1, right? because now I have both of these triggering now. So what's the purpose of this circuit then, and why are we teasing you by saying, well, wait a minute, there's a glitch here with this big red question mark saying, really? Yeah.
Because X should be 1 for a little bit if all the inputs are 1 in reality.
Why?
Because the AND gate's going to have a delay.
There you go. This big lead up I had for going into this slide, right? Talking about all components have some delay. So for some brief period in time, if I set A, B, and C simultaneously to 1 because they're all from the same source, so they would be simultaneously set to 1, B and C are going to take at least a couple nanoseconds to get through that AND gate. In the meantime, A is going straight into that exclusive OR, setting X to 0, until B and C kick in out of that AND gate as the other input to X, and then puts it back to 1, right? Anybody see that? Anybody not see that? Does anybody not see that? That's a very important point. It was a lot easier to see
Basically, we're able to use it for.
when we had numbers in here, right?
Right.
When I put the delay numbers in here, it was pretty obvious. So all I did is just took away those numbers, right? They're still there. There's still delays in each of those components. So we have to bear that in mind when we're doing our design and our analysis, okay? So there are timing dependencies. Although you can design circuits so that there aren't any because you just have these large, what we call gate periods, where these components can all settle, and you're guaranteed, you're assured that all components will settle, and then you sample the output. Okay, if you have that, then you don't worry about delays because you design for that. But if you're not doing that, if you're trying to do instantaneous changes, right, then you have the potential for generating, at least for some period of time, an incorrect output. So if that's what your concern is, if you're worried about instantaneous changes in values and their results, then you have, in this particular design, you have a hazard condition. You have the potential for an error because for a period of time, a brief period of time, that's going to generate, X is going to generate an incorrect result. Okay? That's what we call a glitch. And of course, when we start designing more complex circuits, some combinational circuits, that's the whole chapter, right? It's combinational and sequential circuits. Then those glitches can aggregate. They can combine and create bigger and bigger errors that we have to be careful of. So we need to be concerned about hazards and glitches. All right, so that's what this slide. That's what this slide was talking about. It says, let's go back to our SR latch. Right? Everybody remembers the SR latch. We spent a good deal of time talking about SR latches, right? Yeah, we did. And so here they are. What was the big? Let's go back and remind ourselves, since it's not people aren't jumping up the screen. Oh yeah, that was a really cool gate. What was the big deal with the SR latch that we introduced as some new concept that we hadn't seen up before the SR latches? What was the big difference here?
The output of one was the input of the other, something like that.
Right, we
Circular.
Say it?
Remembering the output, or remembering,
Memory.
saving the output, right?
Right.
Storing the
Yeah.
output.
Yes, it has a stored output. Q and Q nod are going to remember or maintain their values if I take away S or R. This circuit allows us to do that. Yes, we have loops. We've created loops where we have the output of one gate going into the input of another gate. It's vice versa. Actually, both gates are going to send their output to the input of the other gate, which is how we achieve this capability of memory. That's what the SR latch does. It provides memory on the output because we have this circular loop built into it. We also now know that since the output of each of those NOR gates is a function of a direct input and the input or the output of another gate, we also now know that there is a there is a potential hazard in this circuit, right? It could have a glitch if we're not careful with our timing. We don't design that into our circuits. So we have the capability of a glitch with an SR latch. We have a hazard condition, okay? And I think based on what we just saw in the previous slide and looking at this now, we can say, oh yeah. And actually, hopefully, it sort of flashes back to Monday's lecture a little bit where I intentionally talked about, I have this output here, and then I went back and talked about it as an input to the other gate. That is exactly why I elaborated on that point, was because I wanted to make sure everybody understands that it's taking time to go through the gate. It seemingly simultaneously appears as input to the other gate, but it takes time to go through that gate too. So while it's propagating through the second gate, the answers for these gates already appear on Q and Q naught. So there is a moment in time when these may have incorrect results, right? And that time is however long it takes to get through the second component. Okay, and then you can walk through here and everything else is the same. Make sense? Yes?
Could you go have like both go low in the second to last row?
Can I have both go low?
Yeah, could you explain how that happens?
Okay, so to do that, let's go ahead and walk through it then. We have initial conditions, R and S are both 0. We don't know what Q is or Q naught is at this point because it still remembers whatever state it was in before. Okay, no idea. But now I wanted to set R to 0 and S to 1. R to 0 and S to 1. Okay, so what happens there is if I set S to 1, then Q naught goes to 0. Right? That propagates as an input to Q, but it already has its other input, R being 0, so it's already outputting a 1. So I have 1 and 0. I have 1 for Q and 0 for Q naught. Now, if I take away S, right, it doesn't change the outputs because because S is already, it had 1 here before, so it's putting out a 0, so it's going to change, but the other input is already remembered as a 0, so it's putting out a 1, so we have 1 and 0, no change there. Now, I come and set R to 1, and S is going to be remaining at 0. I just remembered, we did this on this board here. Sure, that's the one board they would have erased. Look at that. All right, because this is really the only way you can do it. You got to set these bits here. Q naught, Q, R, S, and then I have U down here, and U down in here. Sorry, get a little stop. Okay, so don't know, don't care what these were before. But I come in initially with 0, 0, 0. Oops, these are. Nobody's out there saying, wait a minute, those are NORs, not ORs. Okay, so I put in a 0, that means this is going to put out a 1. Regardless of what that side's saying. I put in a 0 here. I don't know what this is yet, so I really don't know what this output is yet. So let's follow this one here. Oh, it's a 1. So that means this is going to put out a 0, a 0, and a 0. The 0 doesn't mean anything, right? It's got a 1 here, so that 1's going to pump it to 0. So I got a 0 coming out here, I got a 1 coming out here. Fine, I got that first set. Now, I take away, no wonder. S was supposed to be 1. S is 1. Right?
Yes.
S is 1, R is 0. So S is now going to change that to a 0. That makes that a 0. That's a 0 there, so this might be a 1, we don't know, because we don't know what that leg is yet. The fact that this is a 1 tells me this is going to be a 0. So that means that's a 0. Oh, 2 zeros in, that means I have a 1 out, so I have a 1 here. 1, 1. So that 0, 1 is going to pump out a 1, 0. I take away this 1. This now goes to 0. And since, 1, 1, right? So I took away this 1 here. I leave that at 0 here, but I still have a 1 here, right? So 1 and 0 means this is a 0 still. This is 0 still, so no change. It remembers. That's the memory thing we talked about. So now we change the other bit, right? Leave this one to 0, set this one to 1. Set that 1 to 1. A 1 and a 0 is going to then trip this to be a 0, which instantaneously changes this to 0, which then forces this one to change to 0. That's going to drop this output from a 0 to a 1. And now this becomes a 1. Right? Okay, so far so good. Now I take away this 1 here. Makes that a 0. A 0, 0 here. Changes this to a 1, which changes this to a 1. Changes this to a 1. Changes that to a 0. Changes that to a 0. Right? And now, what happens if I set these both to 1s? So if I instantaneously change these both to a 1, like this, then instantaneously, this 1 is going to drive that to a 0. This will set to 0. This 1 here will drop this to a 0, which will then change this to a 0. Right?
Yeah.
So it forces both of these to go low. But look what happens. When this 0 propagates here, what happens? Anything?
No.
No, nothing happens. And likewise, this 0 here propagates to here. Does anything change here? No. Nothing happens. So if I now change both of these to 0s, look what happens. 0, 0 forces this to a 1, forces this to a 1. 0, 0 forces this to a 1, forces this to a 1. Q and Q not cannot be both cannot. Q and Q not cannot. And here we go again. Those two cannot. These are unequal. They're opposites. They must be opposites. 1 and 1 are not opposites. My system is unstable. I've now walked into this situation where I can just go back and forth. Yes.
How was that able to go into non-opposites with 0 and 0? Then?
Just like we walked through. Because this, when I got it into that state where both of my outputs went to 0, I then created the unstable situation.
And we don't want that, right?
Cannot have that. All right?